In this video, we're going to talk about how to solve boundary value problems. So I want to begin with an example. So suppose that we have the following differential equation. We have, in part A, we have y double prime equals negative 4y. And we have these two conditions. So these conditions that we have, these conditions are purely on the original function y. Not on the derivative, not on y prime. Like we saw with initial value problems, we were given a condition, so we were plugging in the same value into the original function y and into the derivative y prime. But with the boundary value problem, so I'll be abbreviating these as BVP, we're given information about what's happening at two different inputs. In this case, what's happening at pi over 4 and 3 pi over 4. So let's begin by solving our differential equation. Looking at this at first glance, it might not look like it's homogeneous, but because one of the sides isn't equal to 0. But we can easily get it into that form if we move everything to one side. So for example, if I do that and move everything to the left, we get y double prime plus 4y equals 0. And now we could write down the characteristic equation. So for this, it would be r squared plus 4 equals 0. And then that means that r squared equals negative 4. And square rooting this, we get r equals plus or minus 2i. So we have two complex roots to our characteristic equation. I can think of this as being 0 plus or minus 2i. And that's helpful because it lets me identify what the alpha is. That's the real part, and what the beta is. That's the imaginary part. It's just the coefficient of the I here. So remember that the general solution, when we have two complex roots like this, looks like y equals c1 times e to the alpha t cosine of beta t plus c2 e to the alpha t times sine of beta t. So if we plug into this for our specific problem, we get y equals c1, but alpha is 0 for us, so e to the 0t is just going to be 1. So we don't need to write that. So we'll still have cosine of, and then beta is 2, so 2t. And then the next term is plus c2. The e, again, goes away because it just becomes 1. And then we still have sine of 2t. So that's our general solution. Now we need to figure out what c1 and c2 are using these conditions that were given, these boundary conditions. So we know, for example, that y of pi over 4 equals 3. And that is equivalent to writing down, let's plug in pi over 4 into our general solution. That'll give us c1 times cosine of, so 2 times pi over 4, that is pi over 2. And then we get plus c2 times sine of pi over 2. And when we plug in pi over 4, like we did, we should get out 3. So we should get that this whole thing equals 3. So we could simplify this, because cosine of pi over 2 is just 0. And sine of pi over 2 is just 1. So what we're left with here is c2 equals 3. Because sine of pi over 2, that just equals 1. All right, so we know what c2 is. Now let's use the other boundary value condition. So we have y of 3 pi over 4 equals negative 3. And that is equivalent to saying, if we plug 3 pi over 4 into our general solution, we'll get c1 times cosine of 3 pi over 2. That's what 2 times 3 pi over 4 is. It's 3 pi over 2. And then plus c2 times sine of 3 pi over 2. And that needs to be equal to negative 3. All right, so let's simplify this. Cosine of 3 pi over 2, that's 0. And sine of 3 pi over 2, that is negative 1. So what we have is we have negative c2 equals negative 3. Or if we divide by the negative, we get c2 equals 3. So actually, we've gotten the same thing twice. We got c2 equals 3 here, and we got the same thing here. But we have no information at this point about what c1 is. So what that means is that c1 is actually free. It is a free variable. It could be whatever we want. So our boundary value problem solution will look like C1 cosine of 2t, and then plus, and we know what C2 is. It's 3, so 3 times sine of 2t, where C1 is any real number. So our solution to our boundary value problem looks like this. So notice here, because C1 can be anything, there are infinitely many solutions. So that's something that can happen with a boundary value problem. There can be infinitely many solutions. All right, so let's do another example, something really closely related to this. What if I just change one of the values? So I have the same differential equation here in part B. The only thing that I've changed is now y of 3 pi over 4 is equal to 0. So because we have the same differential equation, the general solution to the homogeneous form will be exactly the same. So let's plug in our conditions. So if we look at y of pi over 4 being equal to 0, that is equivalent to, now if we plug in pi over 4 into this, we'll get C1 times 0 plus C2 times 1, so it's the same thing that we got above, and then equals, whoops, I think I miswrote this. This one was supposed to be equal to 3. So this whole thing needs to be equal to 3. So this tells me that C2 is equal to 3. And now let's plug in our other boundary value. So we know that y of 3 pi over 4 is supposed to be 0. And that is equivalent to saying, so if you plug in 3 pi over 4, you'll get C1 times 0 plus C2 times negative 1, just like we got above in part A. And that needs to be equal to 0 this time. And if we simplify this, we get that C2 needs to be equal to 0. So if we look at what we've gotten so far, we got C2 equals 3 and C2 equals 0. That doesn't make sense. That's actually impossible. It's impossible for C2 to be both 3 and 0 at the same time. So because of that, there is no solution here to our boundary value problem. So sometimes boundary value problems have no solution. So, whoops, I had written that twice. Okay, that's all right. No solution here. So in general, boundary value problems can have a unique solution. That's definitely going to be possible as well. Infinitely many solutions, like we saw in part A, or no solution, how we saw in part B. All of these are possible with boundary value problems. In contrast, like we saw in the last video with initial value problems. So we looked at the initial value problem for our second order homogeneous equation with constant coefficients. And when we had these initial values, we saw in the last video that such a problem always had a unique solution. And that's a key distinction between initial value problems and boundary value problems.